Enceladus, the geysers that shouldn't exist. A small moon is leaking an ocean into space, not metaphorically, literally. From fractures near its south pole, material erupts outward in towering plumes, water vapor, ice particles, microscopic grains, spraying hundreds of kilometers above the surface. The moon is only about 500 kilometers across, and yet it behaves like something far larger, far more active, far more alive. Enceladus orbits Saturn quietly, embedded within the planet's vast ring system. It should be frozen solid. It is not. For decades, small icy moons were assumed to be geologically dead, too small to retain internal heat, too far from the sun to sustain melting. Their interiors were thought to be cold, relics left over, building blocks of the solar system. Then the Cassini-Huygens spacecraft arrived in the Saturn system in 2004, and Enceladus changed everything. Cassini detected a faint but persistent plume of material emerging from the moon's south polar region. High-resolution imaging revealed fractures in the ice crust, long, warm cracks now known as tiger stripes. From these fractures, jets of material were erupting continuously. This was not impact debris. It was ongoing activity. What powers the plumes? Enceladus is far too small to generate sustained internal heat from radioactive decay alone. Its volume is limited. Its thermal budget should have dissipated billions of years ago. Yet the surface near the South Pole is measurably warmer than surrounding terrain. The leading explanation is tidal heating. As Enceladus orbits Saturn, it experiences gravitational flexing. Its orbit is slightly elliptical, meaning the gravitational pull varies during each revolution. That changing pull stretches and compresses the moon's interior. Friction from this flexing converts orbital energy into heat. Over time, that heating can maintain a subsurface ocean beneath an icy crust. The ocean remains liquid not because of sunlight, but because gravity needs the moon from within. Clue 1. The jets themselves. Cassini flew directly through the plumes. Instruments detected water vapor dominating the ejected material. Tiny ice grains were also present, along with trace gases. The jets are not random bursts. They vary with Enceladus's orbital position. When tidal stress is strongest, plume intensity increases. When stress relaxes, output decreases. This suggests the fractures are connected to a pressurized subsurface reservoir, not a shallow melt pocket. A global ocean beneath tens of kilometers of ice. The geometry of the eruptions, their persistence, and their orbital modulation all point toward internal liquid water. Clue 2. Salty particles. Cassini carried a cosmic dust analyzer. When it passed through the plumes, it detected microscopic ice grains containing sodium salts. Salts imply interaction between liquid water and rock. On Earth, salty water typically indicates water has circulated through mineral-rich material, dissolving compounds before re-emerging. For Enceladus, this suggests that the subsurface ocean is not isolated from the moon's rocky core. It may be in contact with it. That interaction could allow hydrothermal processes, chemical reactions, driven by heat at the ocean floor. The evidence is indirect. It is based on composition analysis of ejected particles. But the presence of salts strengthens the argument for a chemically active ocean. Clue 3. Organic molecules. Cassini's instruments also detected simple organic molecules within plume material. These were not signs of life. They were carbon-based compounds, molecules containing carbon, hydrogen, sometimes oxygen or nitrogen. Such molecules can form through purely chemical processes. But their presence matters. Liquid water, energy source from tidal heating, chemical building blocks. These are the ingredients considered essential for habitability as we understand it. The wording here must remain careful. Cassini did not detect life. It did not detect organisms. It did not detect biosignatures. It detected chemistry consistent with an ocean, interacting with rock and containing organic compounds. That is extraordinary enough. Enceladus is small. Its gravity is weak. Material escaping from its surface contributes to Saturn's E-ring, a faint diffuse ring of icy particles sustained in part by these plumes. The moon is actively reshaping its planetary environment, and it is doing so continuously, not as a relic, as an active world. There is something almost defiant about Enceladus. It is too small to behave this way, too distant from the sun, too fragile by classical expectations, and yet it vents an ocean into space. The most astonishing part is accessibility. On Europa, another ocean-bearing moon of Jupiter, sampling the ocean would require drilling through kilometers of ice. On Enceladus, the ocean comes to you. You can fly through it. You can collect particles. You can analyze them directly. Cassini proved that. And then the mission ended. No dedicated follow-up mission has returned. No probe has sampled those plumes with next-generation instruments capable of deeper biochemical analysis. We have, in principle, a natural cryovolcanic pipeline, ejecting subsurface ocean material into vacuum, where it can be captured without landing, drilling, or melting. And yet we have not gone back. Enceladus forces a deeper question about planetary science priorities. If an ocean world is venting material into space, and that material contains water, salts, and organics, what are we waiting for? Is Enceladus a rare anomaly, or one example of a class of ocean worlds more common than we once imagined? The solar system once appeared simple: rocky inner planets, gas giants beyond, frozen moons in the outer darkness. Now the picture is more complicated.